Welcome to Generative Camera Dolly, Extreme Monocular Dynamic View Synthesis. First of all, what is a dolly? It might be an uncommon word for some of us, but once you figure out the meaning, your reaction might look something like this. Because this shot is called a dolly zoom, and it was created with a camera dolly, unsurprisingly, which is basically a platform on reels used in filmmaking to create smooth camera movements over time. But would it not be cool if we could do away with all of this equipment and instead use computer vision to perform visual storytelling? So, given any video, what if we build a model that is able to reimagine and reproduce that scene from a different perspective? We also want to be able to freely choose and control that viewpoint after the fact, as if we were operating a virtual camera dolly. So, the end goal is essentially to capture the dynamic 3D environment based on just one input video. This naturally falls under the umbrella of novel view synthesis, and I'm going to simplify a bit by saying that the existing work here can be broadly divided into two categories. On the left, we have seen a lot of amazing progress recently in image to 3D, or novel view synthesis for objects. Given a single input photo, these models can generate images of all the different sides of that object, including the back, for a downstream 3D reconstruction. On the right, we add a time dimension, so we have dynamic view synthesis for scenes. Most of these methods carefully and iteratively optimize a 4D reconstruction, after which they can render high-quality videos from novel viewpoints, albeit with relatively limited camera viewpoint displacements. These works often have impressive results, but since they tend to train for each scene separately, it makes them a bit slow, and it also prevents them from learning generalizable priors or useful knowledge about the world that can be shared across different examples. So the natural question is, can we do something that somehow combines the best of both worlds? Specifically, how should we accomplish view synthesis for dynamic scenes based on a single video that takes less than a minute and works for more extreme perspective changes? This is actually a very tall order if we think about it, and I want to share two important thoughts with you at this point. Number one, we're going to need precise camera pose control if you model the problem in an end-to-end fashion without intermediate 3D geometry, then we still need to condition it on camera transformation parameters. Number two, this is at its heart essentially a video-to-video translation problem. And we know what the state of the art in visual synthesis is, right? Today, it is largely embodied by diffusion models. And we also know that modifying diffusion models in order to teach them new skills, such as ControlNet or 0 to 3, has been proven to be a very fruitful paradigm. So, we take a state-of-the-art open-source generative video model, in this case stable video diffusion, and we modify it in order to accommodate the new types of conditioning that we need, which are a camera matrix and the input video from the source viewpoint. The core idea is then that by training not from scratch, but instead from the provided image-to-video checkpoint, we essentially establish the roots of our framework in existing representational powers of a very large-scale pre-training stage that happened on all kinds of video data from the internet. And then we channel those priors towards this new task that links together videos from different synchronized camera viewpoints with each other. So this whole thing is trained on multi-view video, and we contribute two different data sets in this context. The first one is based on the Google Kubrick simulator with many dynamic objects undergoing various complex motion and occlusion patterns. The second one is called Parallel Domain, which is also synthetic and has thousands of high-quality diverse driving scenarios. Let's take an initial look at some results on the test sets. In each case, we choose a set of angles randomly, and we ask the virtual camera to gradually rotate or move towards that desired perspective. And even though these videos are not perfect, given the extremely difficult nature of the task, I think the results are definitely decent, right? Specifically, the geometry, the visual appearance, and the dynamics of the objects are well respected. We also compare qualitatively and quantitatively against several baselines. First, in our model on the right, you can see that despite heavy occlusions, all the objects remain reasonably consistent both across views and time. On the lower left, we show 0 NVS, which is roughly speaking 0 into 3 for scenes. On the lower right, we have hexplane, which is roughly speaking a more efficient version of dynamic nerve. We found, in fact, that hexplane has to have about 16 different viewpoints available as inputs to reach a similar performance as ours from just one viewpoint. Here are driving scenes, where we shift the camera backwards and upwards. With our framework, we can predict either visual colors or semantic categories. And even though some artifacts are visible, the results are still quite solid, because when you look closely, you'll notice that there are many occlusions going on between the different objects. Let's now turn to the real world. If you look at the input video on the left, both the blue and the red duck are getting fully occluded. This is, of course, related to object permanence and intuitive physics, which are very challenging problems in computer vision. So I think it's very cool that our model predicts the correct outcome in this case, which suggests that it actually learns the necessary spatio-temporal reasoning skills in order to estimate the for the scene contents as well as possible. Some more real-world examples are shown here. Imagine you are a robot and you want to see what the consequences of your actions are. Well, then it makes sense to use our model and predict various synchronized viewpoints in order to essentially maximize your situational awareness as you are actively manipulating the scene. So to summarize, this was generative camera Dolly. We devised an approach that essentially conceives a virtual camera that can move around freely based on just a single physical camera. I think there are many promising future applications here in terms of building better for the scene representations or learning world models for embodied AI, and possibly even VR or spatial computing. We also publish high-fidelity multi-view video data sources. And finally, because our approach is basically surfing on top of state-of-the-art generative models, there are very good reasons to believe that it is scalable, and we will keep improving over time along with the quality of the underlying representation, as well as the size of the model data and compute capacity. And finally, please feel free to check out our webpage for many more visualizations, including failure cases, as well as links to the source code, datasets, and pre-trained models. Our poster number at ECCV is 156. Thank you very much for your attention.